Yes, so first of all, good morning everybody. Thank you for getting up so early to see this presentation and hear about the EvoSep One system that we had in the lab for about a little bit more than 4 months now. So we got the first one installed in January, and in February we made the first gradient optimization, and now in the beginning of May we have the second gradient optimization, and basically the instrument now is in full production mode in the lab. This is what it looks like. We're running it with our Exactive HF-X instruments. And maybe I should just mention that all the slides that you will see now, all the work has really been done by Dorte Becker-Jensen in the lab, who has basically been generating data up to yesterday, where she gave birth. So it's really fresh data from somebody that's had a lot of pressure. We, as I mentioned, we use it in front of the Exactive HF-X system, which is the latest generation of the Exactive mass spectrometers, in which there's been a number of improvements compared to the previous generation. So there's a brighter ion source now. The ion optics and transfers have been optimized such that we can actually now do much faster scanning on this instrument. And that basically makes couple of very fast scanning methods available, where we can go with either 41 Hz ACD fragmentation or 28 Hz ACD fragmentation, but also with very low fill times. And when we tested this, we realized that these very fast scanning methods, they work extremely well with short gradients. So when you have short gradients, you can actually achieve more than 1,000 peptide identifications per minute of analysis time using these very fast gradients. And of course, that kind of fits very well with the EvoSep system, so we thought that this would be a nice system to try to benchmark against our standard easy nanorods and 1200 system that we use normally in the lab. And so far we've been using it with these type of 15-minute gradients, but unfortunately with the loading and the equilibration of the columns and the washout, we typically have overhead time of almost twice or more than the actual analysis time, gradient time. So a 15-minute gradient typically translates into something like more than half an hour of run-to-run time. So we thought that with the EvoSep system, it would be interesting to see if we could reduce this run-to-run time and but still basically achieve the same peptide identification space. And that's indeed what we saw, that using the so-called 24-minute gradient on the EvoSep One system, where we get 16 minutes of peptide elution, we can basically see more or less the same number of peptides per second as we can do with the ECLC system. Except we noticed that in the early parts of the gradients, we didn't really have the same number of identifications as we saw with the ECLC systems. And therefore, we went through a couple of iterations to optimize the gradient together with the guys from EvoSep. And we can actually see now that with the new optimizations of the gradients, so you can see this is the original gradient, and with the first optimization, and now with the second one, we really are maximizing also the identification rates in the early parts of the gradients. And that also nicely translates into that we actually get sharper peaks. So the median full width half maximum of all the precursors are also getting in the range of what we normally see on the EvoSep or on the ECLC system. And basically, when we now just analyze our standard Hela samples digest on the systems, we can see that we achieve more or less the same number of identifications as we do on the EvoSep on the ECLC system. So from the initial gradient and now up to the optimized second gradient, we can see that we're actually very close. So it's mainly on the longer gradients that we see a slight difference in number of identifications. But that's also where we see the least benefit from the EvoSep system is when we go to longer gradients, then the overhead time, of course, also becomes more and more neglectable from the ECLC system. So it's really with the short gradients that we have the maximum benefit. So we are very happy with the run-to-run reproducibility. It's more or less in the range of what we also see on the ECLC systems. we can see that we have very consistent pressure profiles. So this is an overlay of 350 consecutive runs, and you can see we have exactly the same profiles of the systems, and we typically have very good correlation between the intensities from run to run. So this is exactly what we need in our everyday work. We are of course a little bit worried about the sensitivity of this system, given the fact that we are now running with up to 3 times or more higher flow rates compared to what we normally do on the ECLC systems. But actually, we don't really see a major loss in sensitivity when we go from the normal 500 nanogram on column down to even 50 nanogram on column. It's actually only again at the longer gradients where we see some kind of dilution effect when we use lower amounts of material on the column. So in our lab, we like to use very massive offline fractionation to get very deep proteomes. So we typically do offline high pH fractionation where we collect up to 46 fractions, and then we analyze each of them online with low pH LCMS on the Exactive platform. And for that one, we traditionally again use the EC-NLC system, and with those and on the short gradients, we can see that we have a lot of overhead time. So to run all 46 fractions, that sums up to something like 28 hours of mass spec time that we need to spend. But on now, with the EvoSep One system, we can see that in just 18 hours, so we're basically saving 10 hours of analysis time, we can achieve more or less the same number of peptides and protein identifications. So we're very pleased with that. And usually, what we also have to do on the ECLC systems is actually between all these runs, we need to perform a number of washes really to clean up the columns. But we can see with the EvoSep system, we have very little carryover, and therefore we can basically avoid the washes as well. So we can almost cut the analysis time in 2 when we use these systems. So we also now very fond of the so-called data-independent acquisition strategies. Especially for these short gradients, we can see that the number of peptides and proteins that we can identify using the DIA strategy compared to a PDA strategy seems to be very beneficial. So on this our original paper describing the Quantitative HF-X, we showed that with the DIA strategy, just 30 minutes of analysis time, we could actually quantify close to 6,000 proteins from a Hela lysate, will be at the same time would only get close to 4,000 proteins if we analyze it with data-dependent acquisition. And now when we use the EvoSep system with the 21-minute gradient, or under we can do 60 injections per day, we can actually identify close to 50,000 precursors and 40,000 peptides, and something around 2.5 or 5, a little bit more than 5,000 proteins. And we again see a pretty good reproducibility from run to run. So we're very excited about this possibility to really do very fast DIA applications. And again, for DIA, it's we're of course interested in getting as low CDs as possible on the peptides that we identify, and therefore we often end up in this kind of trade-off situation. If you want to have good quantitation, then you need to scan faster, have faster scan cycles, but that typically then leads to lower number of identifications. But if you want to maximize the number of identifications, you need to have longer scan cycles, but that then usually ends up in having less precision in the quantitation. But generally, we see that with the EvoSep system that it's totally on par with the ECLC system. And again, no matter what kind of amounts that we load on the system, we get very reproducible number of proteins that we can quantify in each run. So we're not only using vapor-free quantitation, we're also doing a lot of TMT-based quantification. But in order to take advantage of the TMT-based quantification, we of course like to couple it with very fast scanning method. And Alexander Makarov and his team in Bremen have published a couple of years ago this new FTLS-based method called phase-constrained spectrum deconvolution for e-transformation of mass spectra, in which they can basically achieve higher resolution with the same transient time. And Christian in my lab set out to test this new feature on the Exactive HF-X to figure out what are the limitations for this feature, what is the minimum required resolution that we need to have in order to basically separate TMT report lines that have the same integer mass. And to do that, Christian basically tested it directly against the traditional enhanced FT methods using the different resolution settings that are available on the Exactive HF-X. And he actually found that on using the normal EFT method, we can use the 64 millisecond method that is equivalent to 30,000 resolution. But with the new Phi-SDM, we could actually go down to only 32 milliseconds transient times for the 15,000 resolution method, allowing us to do very, very fast acquisition now with this feature. And as you can see, that directly translates into an increased number of peptides and PSMs when we can scan faster on the instrument. So we thought we wanted to test this now on the EvoSep system and see, like in a typical large-scale experiment, if we were to now look at 5 different cell lines that we have in duplicates, and we would then label them with the 10 different TMT report lines, and then basically do our standard workflow where we do the 46 fractions by offline fractionation. And we could see that we actually identify more than 100,000 unique peptides or more than 8,500 protein coding genes that we could then very nicely quantify all the proteins and directly see how all the cell lines are compared to each other. So this seems to be a very efficient method to basically look at up to 11 different conditions in just 18 hours of analysis time. We're also doing a lot of phosphoproteomics in the lab, and for many years we've used also the offline high-phase fractionation to get very deep into the phosphoproteome. So we typically use milligrams of starting material and a lot of measurement time on the instruments, and that would then typically be in the order of maybe 40,000 peptides we could identify. But we wanted to optimize this to also have less starting material, do single-shot analysis, and then really have potential for high-throughput analysis. And in the new Exactive HF-X instrument, we've shown that with the fast scanning methods here, the 28Hz method, we can actually identify up to 5,000 phosphopeptides in just 15 minutes of analysis time. So we actually worked a little bit more on the high-throughput system, such that we can now do it in a 96-volt format using these titanium IMAC magnetic leads, which actually seems to be superior to our normal titanium dioxide in the fact that we can identify now more than 10,000 phosphopeptides in just 60 minutes of analysis time. And on the EvoSep system, we see numbers that are slightly lower than on the EC Analyses system, but they're still very much in the same range. So more than 6,000 phosphopeptides identified with these the short gradient for which you can run 60 samples a day. And the nice thing is that we have actually also now transferred this to DIAphospho, such that we can really take advantage of the fast scanning methodology. So we use this setup here, and we can see with DIA we can actually cover many more phosphopeptides compared to a classical DDA mode of operation. And that is simply due to the fact that we are analyzing many more ions in DIA mode compared to traditional DDA mode, especially for phosphoproteomics. So we were of course interested to see how good can we do the DIA phosphoproteomics now on the EvoSep One system, and for that we started off by collecting a spectral library, basically taking Hela cells, digest with trypsin, and then do the offline basic reverse-based chromatography, and collected both 46 fractions and 12 fractions, so that we have in total 58 fractions that we will then again analyze with these 60 samples per day measurements, and then analyze everything with Max1 to generate the spectral library, and then import that into Spectrum for further analysis. And we can see just 5 hours of analysis with the 12 fractions, we actually identify more than 25,000 phosphopeptides on the EvoSep system. And if we use the 46 fractions application, we're close to 50,000 sites. And combined, we have more than 55,000 phosphopeptides that we can now use as our library to match in to single-shot identification runs. And this is just an average of 12 samples that we have now run with the short 22-minute gradient on the EvoSep system, and we can see that in each of the runs we are actually able to identify and quantify more than 10,000 phosphorylation sites. So this looks very, very promising for large-scale phosphoproteomics. We're also interested to see if we can actually use this system to get close to also covering full proteomes, and previously analyzed the yeast proteome in great depth, but that required a lot of fractionation and a lot of analysis time. But a few years ago, the Kuhn lab published this 1-hour yeast proteome paper in which they used 1.3 hours to identify close to 4,000 proteins. And we were of course interested to see if we would be able to use more or less the same strategy for our on the EvoSep system with the high pH fractionation and the DIA workflow. So we again generated a spectral library of yeast based on the 46 fractions. So analyzing, spending a little bit more than 18 hours, we could identify more than 4,000 proteins and 33,000 peptides covering the yeast proteome. And then we basically use that to as the library for all the DIA runs of the yeast proteomes. And again, we could see that with shorter cycle times, that we could get around 3,500 proteins, of which 70% of the CVs were below 20%. But with longer and slower scanning methods, we could get slightly deeper into the proteome, but then we would also suffer a bit on the accuracy of the quantitation. And we can see we're not covering the entire yeast proteome. We're still missing out a little bit on some of the lower abundance proteins, but at least it looks very, very promising that we can quantify more than 3,500 yeast proteins in just 21 minutes of analysis time. Of course, we're also interested to apply the systems now in more disease related applications. So we're involved in a number of EU networks where we are analyzing different tumor samples. And this is in one of them where we look at kidney cancer, where we compare healthy versus diseased tissue that was not frozen from the same patients. And again, we can use the EvoSep One system with the fast gradients. And by building first the spectral library, we could again quantify more than 4,500 proteins per sample, or close to 6,000 proteins altogether. And if we do a t-test analysis, compare the healthy versus diseased, we could see that more than 1,400 proteins seem to be differentially expressed. And this is just the a heat map of the hierarchical clustering, and we can see that, all as expected, that the proteins that are low in the tumors seems to have these gene ontology pathways associated with them, whereas the pathways that are high in the tumors are mainly splicing and functions such as cell-cycle-related stuff. We also recently showed that we can actually do very deep phosphoproteomics using TMT quantitation, especially with the MS2-based methods. And that's also something that we are now applying to screen different cancer types. And in this case here, we're looking at colorectal cancer, where we got 20 tissue slices of 20 microns each. And where we again have this very sensitive workflow where we can do TMT labeling of just 70 micrograms of peptides that we would then split parts of it for phosphoproteome analysis and parts of it for proteome analysis. And again, we can see that with this very nice acquisition, very fast, and the quantitation on the by the TMT labeling, that we can very easily separate the tumors from the normal patients. And again, we can see that the KEC pathways that are overrepresented in In the healthy condition, there's all the things that have to do with what normally is going on in the colon, whereas in the tumor situation, we see again that there's lysosome and ribosomal proteins combining this. And that is also reflected in the phosphoproteome, where we again, using the same strategy, we can actually identify and quantify more than 6,000 localized phosphosites from this very minute amount of material, and more than 2,000 of them seems to be significantly regulated between the tumors and the healthy condition. And here we can see that, not surprisingly, that in the tumors that they have really adapted for growth. So it's the protein-directed kinases and the cyclin-dependent kinases that are significantly overrepresented, whereas in the healthy condition, it's many more kinases that seems to be activated. So with that, I hope I've just given you a flavor of the things that we can do with the EvoSep system. I would of course like to thank all the people in the group that did the work, especially Gordon, and this was done in close collaboration with Philip Beyer and Matthias' group, and also thank the EvoSep team for their help, especially with the tips and tricks on the new system and for optimizing the gradients. With that, I'd like to thank you for your attention. I'll be happy to take questions. Thank you.